Hi, my name is Gerard. I'm a fourth-year student in chemical engineering, and my presentation is on developing a structure-based model for the cathode catalyst layer of polymer electrolyte fuel cells. Hydrogen fuel cells are electrochemical devices and emerging clean energy technologies. They directly convert chemical energy into electrical energy with the reaction of hydrogen fuel and oxygen, producing electricity and water as a byproduct without any carbon emissions. Polymer electrolyte fuel cell is a common type of hydrogen fuel cell, characterized by a polymer electrolyte membrane layer, and is advantageous for its high power density, low weight, and low operating temperature. One of the main challenges for implementing PEFCs is the cost associated with the platinum catalyst used to facilitate the reaction, especially at the cathode side. So to reduce the cost, it is essential to reduce the number of catalysts used to make it an economically competitive technology. So here is a closer look at the cathode catalyst layer. As you can see, it is porous. And here's our expensive platinum catalyst. So we focus on the thickness reduction method of the catalyst layer to reduce the catalyst loading in the cell. However, when we decrease our catalyst loading, we get performance losses, such as what we see in this example. And from previous data, drastic reduction of catalyst loading leads to more unexpected increase in performance losses. We have our own hypothesis on the problem. But first, taking a closer look in the cathode side, we have oxygen coming in and the reaction taking place at the catalyst layer, which produces water in the form of liquid water, or it could be vaporized into water vapor. Finally, both species will need to be removed from the cell, which leads us to our hypothesis. At lower catalyst loading, we have reduced vaporization, which means more liquid water goes through the diffusion media, resulting in higher liquid pressure. This impedes the oxygen transport in the layer, so less oxygen goes through to react, consequently decreasing the performance. This highlights the importance of water balance in fuel cell performance. This stresses the need for a structure-based model that would show the water balance in all components of the fuel cell's cathode side. To do this, we combine component models for the catalyst layer, diffusion media and flow field interface. And so the following assumptions were set. So my work during the summer focused on creating a model for the cathode catalyst layer. It was divided into two stages. First, we modeled the CL with only hydrophilic pores. Then we incorporated hydrophobic pores into our model. The first stage model followed the following sequence. So first, we set the parameters, constants, and variables. Then equations for pore size distribution, saturation, and effective properties were defined. Then a system of differential equations that relate the pressures and the fluxes was defined. These equations are complex to solve, so we use an iterative solver, which makes use of these boundary conditions and this implicit equation. Then we obtain a solution, the variation of these variables with respect to x. Then, using those, we obtain what we call the Q values, which defines the oxygen reduction reaction, the vaporization, and the liquid buildup in the layer. Through these, we can analyze the movement of the three species and the water balance in the catalyst layer. The Q values will also be used to create polarization curves, which will define the performance of the cell. We can also modify our model to accommodate for a special case at very low overpotentials, where additional conditions are set for the cell. For the second stage, the model follows a similar flow, but we added a distinction for the variables and parameters that depend on whether the pores are hydrophilic or hydrophobic. We again defined equations for the pore structure, saturation, and effective properties, but this time we had to make our own equations by modifying the previous equations to accommodate for hydrophobic pores. We used the same system of differential equations and solved them with an iterative solver. But for that, we added an implicit step where we had to determine whether the liquid-vapor interface resides on the hydrophilic pores or the hydrophobic pores, since the equations that we use are dependent on this fact. And a solution is obtained similar to stage 1, as well as the Q values. So with this, we have defined a structure-based model for the cathode catalyst layer to add to our component models. A model for the DMFF interface is also currently being developed. In the future, we want to build a model for the DM, combine the three models, then do some model analysis and parametric studies. Then with these, we can create our polarization curves, and we can analyze how water balance affects the fuel cell performance, hopefully advancing fuel cell design and efficiency, and contributing to the advancement of fuel cells as a clean energy alternative.